can't talk about the average value of a function without discussing the mean value theorem for integrals first. But our end game is going to be finding the average value of a function. So here we have a function f in purple, and we have this area under the curve of f, which we know is the definite integral. And that gives us the exact area under the curve. What the mean value theorem for integrals guarantees is the existence of some x value, which we call c, on the interval from a to b, such that when we go up to f of c and draw a rectangle with that height and a base of b minus a, so the f of c, the height of the rectangle, and b minus a, the length of the rectangle, when we multiply those, we get the area of the rectangle. And the mean value theorem guarantees that that area of the rectangle has to be equal to the area under the curve for at least one value of c on the interval. It's the height of that rectangle, though, that's called the average value. So when we talk about average value, we're really looking for the height of that rectangle. So let's see what that all looks like when we put it all together. We have this c value such that when we do f of c, the height of the rectangle, times b minus a, the length of the rectangle, that rectangle's area will be the exact area under the curve. But the average value is the height, or the f of c. So we solve it for f of c. So consider dividing by b minus a, or multiplying by 1 over b minus a, which brings us to this. The average value of a function is f of c such that it is equal to 1 over b minus a times the integral from a to b of the function. Now this actually does look like sort of an arithmetic average. We're adding up all of our rectangles, giving us the exact accumulated area, and then we're dividing by the length of the interval. So we still have that grand total divided by how much. In this case, it's how far. So I like to think of average value as the definite integral over or divided by the interval. So let's look at this in real context first. So here we have new COVID-19 hospitalizations in Minnesota. And what the mean value theorem for integrals states is that there's got to be some c value. So when I draw a rectangle with height of f of c, I'll have the exact same area as the area under the curve of f. Let's consider this yellow connecting curve, the curve of f in this scenario. I think I would put my c value right about here, because when I draw that rectangle with that height of f of c, you'll notice that the amount I miss under the area of the curve, so all this neon green stuff, will be picked up by the empty space in the rectangle. But the average value is the height of that rectangle right here. How high is it? Let's suppose it's at 90. So that would be 90 new hospital admissions on average over this time period. Now we'd have to make the time period numeric. We'd have to call April 1, May 2, 3, 4, 5, 6, 7, 8, 9, 10. And the width of our interval then would be 10 minus 1, or 9. Okay, so that's what the average value is. It's the height of that rectangle that makes its area the same as the area under the curve. Let's look at 3 examples of finding the average value. We're not going to be evaluating the definite integrals. It's assumed that you've already learned how to evaluate a definite integral with methods that lead up to section 8.1. So we'll just be discussing the setup of the average value. So for this first one here, we specifically have the function w of x. And remember, we do the integral over the interval, or 1 over b minus a, which would be 1 over pi thirds minus 0, which would be just 3 over pi when we multiply by that reciprocal, times the definite integral from 0 to pi over 3. And in the integrand, we'd put our function w, because it's what we're finding the average value of, which in this case is cosine of 4x. And then you would integrate that with methods leading up to this section. And this would not be a calculator active. You'd have to integrate that by hand, and your answer would represent the average value of w on that interval. Next, we have an AP FRQ. We're going to focus here on part C, where we're finding the average value of this piecewise function f on the interval from -1 to 1. Well, again, we do 1 over b minus a, which in this case would be 1 minus -1 or 2, times the integral from -1 to 1. And you might be saying, yeah, but it's a piecewise function. It is, but if we look at them butting up there at 0, and we think of the limit, we would still be accumulating the area up to 0, and then from 0 to 1. So we would just add them up since the function's continuous. And right here is where you would have that proved to you that it's a continuous function. It would have been in part A. So we're just going to add up the two pieces of the piecewise function separately. And then we'd integrate all of these pieces with respect to x. And again, the evaluation of e to the u du with a little u sub and a trig antiderivative and the antiderivative of 1 being x all comes from our unit 6. So lastly, we have velocity and acceleration in a motion problem, where we're finding the average velocity, where the velocity is defined up here, of a particle from 0 to 6. And again, we do 1 over b minus a times the integral from a to b of the function of which we're averaging, and we're doing average velocity. So our velocity would go in the integrand. Sometimes students like to put the acceleration in there because they think, well, the antiderivative of acceleration is velocity. But remember, we've got this dividing by 6 happening here, and this represents 6 time units. So if our velocity was in feet per second, with a little unit analysis, this would have been feet for our v of t per second. Our change in time, or our dt, is in seconds. So when we do its antiderivative, we do get position, but then this division by 6 is right back to dividing by seconds. So we're back to feet per second, and it does give us velocity units. So think of that unit analysis. And then what we would do on this one was calculator active. I believe this was 2011, if I'm not mistaken. We would go to our calculator and make sure that we have our velocity entered. And then I would use my Math 9 and my bars to bring it in. Okay, and the answer would be 11.696 for that one. So our next video, we're going to be looking at 8.2, where we'll be moving on into more problems involving motion and integration.